What comes out of an offshore well is not ready for the market. It blasts upward from the reservoir as a dark, turbulent, multi-phase fluid. This stream is a chaotic mixture of crude oil, natural gas, formation water, and abrasive sand. It arrives at the wellhead under crushing thermodynamic conditions, sitting at pressures up to 3,000 pounds per square inch, roughly 200 bar. In this raw, high-pressure state, the fluid cannot be accurately metered, it cannot be pumped efficiently, and it cannot be transported through 100 miles of subsea export pipeline. The offshore process plant exists to execute a precise thermodynamic and gravitational decoupling of that fluid. To achieve this, engineers utilize a massive, interconnected macro-architecture. The lower sections isolate the liquid processing, utilizing high and low pressure separators to stabilize the crude oil. The upper sections handle flow assurance, routing gas through scrubbers and compressors for transport. Meanwhile, dedicated lines send a portion of gas back down into the reservoir for enhanced oil recovery, maintaining pressure to keep the well flowing. The offshore platform functions as a live phase and pressure engine, the only mechanism capable of forcing geological chaos into predictable, stable export commodities. The separation process begins with a mandatory pressure drop. The well stream must be depressurized to allow the intermingled gas to break free from the liquid oil. If you drop the pressure all at once, say from 30 bar straight down to 1 atmosphere, the result is violent. The dissolved gas flashes instantly, creating heavy foam and forcing liquid to surge upward into the gas outlets. That liquid carryover travels downstream and enters the gas compressors. Compressors are designed strictly for vapor. Hitting them with dense liquid droplets causes catastrophic mechanical destruction. The engineered solution is a controlled, stepped pressure cascade. By staging the pressure reduction across a series of vessels, the gas releases gently, protecting the downstream machinery. The primary vessel in this sequence is the horizontal 3-phase separator. As the high-pressure well stream enters the vessel, it strikes an inlet diverter baffle. This physical barrier abruptly kills the fluid's forward momentum, forcing the initial separation of heavy liquids from lighter gases. From there, gravity stratification takes over. Because of their varying specific gravities, gas rises to the top of the vessel, heavy formation water sinks to the bottom, and the oil floats securely in the middle. An internal weir plate acts as a physical dam. The floating oil continuously spills over this weir into a dedicated collection section, while the heavier water remains trapped behind it. Above the liquid, the escaping gas passes through a demister mesh pad. This pad coalesces microscopic liquid droplets, ensuring they fall back into the liquid pool before the gas exits the vessel. The separated oil then flows into a series of low-pressure degassing drums, systematically stripping out the final traces of dissolved gas. Once stabilized, this oil meets the export pumps, which elevates its pressure back up to 750 psi, forcing it into the subsea pipeline network. This multi-stage separation process yields dead crude, a liquid stripped of volatile gases, rendered stable enough to survive the physical stresses of long-distance transport. While the crude oil is now stable, the separated gas stream presents a different engineering hazard. As it exits the separators, it is completely saturated with water vapor. If this wet gas enters a cold, high-pressure subsea pipeline, it faces immediate thermal shock. This phase envelope graph plots pipeline pressure against temperature. The shaded region indicates the hydrate zone, the exact conditions where high pressure and near-freezing seabed temperatures intersect. When the gas stream crosses into this zone, the water and hydrocarbon molecules physically lock together.
They form hydrates, solid ice-like crystalline structures that rapidly aggregate and can entirely block a pipeline. The first line of defense is chemical flow assurance. Engineers inject inhibitors like monoethylene glycol, or MEG, which alter the fluid's chemistry to shift the hydrate formation threshold to a lower temperature. However, exporting gas directly to onshore refineries requires a stricter solution. The gas must be physically stripped of its water entirely. To achieve dry gas export, platforms rely on a triethylene glycol, or TEG, dehydration system. Inside the vertical contactor tower, countercurrent physics drive the dehydration. Wet gas flows upward from the bottom, while dry, lean glycol cascades downward across multiple trays. Bubble valves on these trays force the rising gas to physically percolate through the liquid glycol. The glycol acts exactly like liquid blotting paper, absorbing the water vapor directly out of the gas stream. The gas exits the top dry and ready for export, while the water-saturated, rich glycol pools at the bottom and is routed to a regeneration reboiler. The reboiler's job is to boil the trapped water out of the glycol, so the chemical can be reused. But this creates a severe thermal constraint. To guarantee the water vaporizes, the temperature must reach 200 degrees Celsius. At 204 degrees, however, the TEG chemically breaks down into highly corrosive acids. Plant operators must thread a razor-thin 4-degree margin of error. The workaround relies on partial pressure. By injecting a stream of dry stripping gas into the boiler, engineers artificially lower the partial pressure of the water vapor. This pulls the water out of the glycol at lower temperatures, achieving 99.9% purity without ever crossing the thermal limit. Without this thermodynamic manipulation of glycol and partial pressures, the formation of solid hydrates would rapidly render multi-billion-dollar pipeline networks physically impassable. Extracting fluids topside is only half the engineering equation. The other half occurs thousands of feet below the seabed, inside the reservoir rock. This chart tracks reservoir production decline. As oil is extracted, formation pressure falls, approaching the minimum flowing wellhead pressure. Natural drive extracts only 10 to 30% of the oil before pressure drops below this threshold, causing production to flatline. To extend the life of the field and keep the fluids moving, operators must implement enhanced oil recovery, or EOR. The dominant EOR strategy is peripheral water injection, pumping treated fluid down to restore reservoir pressure. Engineers drill wells into the formation's flanks. Forced into the periphery, water physically displaces the remaining oil, driving it horizontally toward the central production well. The most abundant source of injection fluid is raw seawater, but pumping untreated seawater underground introduces a severe chemical hazard. It contains high levels of dissolved oxygen, typically around 9.25 parts per million. Injecting that oxygenated water causes rapid downhole pipe corrosion. Worse, it feeds sulfate-reducing bacteria in the rock, which multiply and sour the reservoir with highly toxic hydrogen sulfide gas. Before a single drop of seawater enters the injection well, it must undergo aggressive deoxygenation. Many platforms use the Minox deoxygenation system, a compact alternative to vacuum towers. Seawater passes through static mixers, where a methanol catalyst triggers a reaction, crashing oxygen from 9 parts per million down to less than 10 parts per billion. The offshore platform operates as a closed thermodynamic loop. Engineers meticulously decouple fluid phases topside to extract the product, while aggressively engineering pressure back into the lithosphere to ensure the system survives.